All right, let's see what we got going on for the third part. So I already said that the third part are those polyatomic ions like nitrate. So I've got some hints for you how to memorize those. Oops. Okay. So one of the things with polyatomic ions, we've already talked about, if you need more than one, you have to put parentheses around the whole thing. By the way, sometimes I run into students that for some reason in the polyatomic ions like nitrate, they want to go ahead and put the charge there. No, you don't put the charge. But if you need more than one, you have to put parentheses in the lower right-hand corner. You put outside the parentheses how many you need. Okay, so can you guys find this sheet? Okay, now if you would add, this says the title of the sheet is common anions. I want you to add 2 polyatomic cation ions, so 2 positively charged ones. And we've run into them, one today and one yesterday. So NH4 plus 1, that is ammonium. And one of the most irritating polyatomic cations I know is this one. What does the symbol Hg stand for? What element? Mercury. Yep. So one of the things that mercury does is it is like a kind of a diatomic sort of thing. Okay, so it's got a covalent bond there. It runs around with a +2 charge. Just strange. Okay, so this right here, actually, let me move this over, is Hg2 2+. So it's polyatomic in that there's 2 mercury atoms that make it, and they're collectively running around with a +2 charge. Now you can't break it. Just like up here, ammonium, it's got a central nitrogen atom, 4 hydrogen atoms, all running around with a +1 charge. You can't break that either. So you can't break those bonds, and you can't break this bond with normal, ordinary sort of exchange reaction. So the name of this, and don't blame me, is mercury, because it's mercury, and then Roman numeral 1, mercury 1. So go ahead and put that on your sheet. Hg2 2+ is the mercury 1 polyatomic cation, so you can't break it up. Well, you can, but it doesn't work that way. Okay, so otherwise, the sheets you have there are all negatively charged. Now, we talked in part 1 about monoatomic, I'm going to pick on the nonmetals, monoatomic nonmetals that pick up an electron or so to become like the rare gas in their same period. What do they end with? What is the suffix? So like, for instance, instead of chlorine, Cl-1 is chloride with a D. Now, I don't know how you guys need to get it here or get it here, but IDE means 1 atom. Okay. So now on to part 3. What does this look like? So I had you put these 2 on your sheet just a minute ago. So ammonium and it's NH4, those 5 atoms running around collectively with a +1 charge. Hg2 2+ is mercury 1. Most of the polyatomic ions actually have oxygen in them. There are some exceptions. So look where carbon is on that sheet, where carbon is. And do you see a Cn-1? Okay, so that's how your little sheet works. It kind of focuses around an atom. So Cn-1, you're going to have to memorize cyanide. SCN-1 is thiocyanate. How do you memorize it? You just will. I3 with the -1 charge is triiodide. You're going to want to memorize hydroxide, OH-1. Again, cyanide, triiodide. So if you look at that sheet, if you look where sulfur is, and if you look where nitrogen is, you're going to see that they combine with different numbers of oxygen. For instance, sulfur can be an SO3, and we're less familiar for some reason with that. That's called sulfite. And sulfur can be an SO4, sulfate or more. That one kind of rolls off our tongue more likely. I will be looking very closely because just for kicks, tell me what is sulfide. What is that? It's just the one atom. It's S2 minus, exactly. But when you look at this kind of, if you want to cluster these together, which I do encourage you to do, a few things. Do you see that they have the same charge? You're going to have to memorize the charge. It's -2. And the other thing is in a cluster like this, in this case sulfur, the one that has more oxygen, it will end in ATE, will be the suffix. Less oxygen will be ITE. And I always remember I ate more oxygen. Okay, but now that's only relative to, in this case, sulfur. If we switch gears and go to nitrogen, nitrogen has 2 oxyanions. It has an NO2 and an NO3. Which one is the 8? The NO3. Okay, again, within this cluster. The one that has the less oxygen ends in ITE. And they have the same charge, -1, relative to each other. So you're going to somehow have to kind of, I really think chunking is going to help. Okay. Oh my goodness. So the halogens, of course, halogens are 7A. Chlorine, bromine, and iodine all form the set of 4 oxyanions. I'm going to kind of help you give a clue to how that works. The 2 that are kind of in the middle, where they're combining with 2 oxygens and 3 oxygens, go with the rule I just told you a minute ago. So this would be chlorite, and this is chlorate. Now, if you are dying of heat loss, we call that hypothermia. So you have less thermal energy than you should have, hypothermia. So something like that. So if we have an oxyanion as one of these halogens that has less oxygen than the ite, so instead of 2, it's 1, ClO, okay, it's hypochlorite, okay? And then if it has more than the 8, we again add a prefix. Instead of hypo, it's per. So we have perchlorate, a little bit more than chlorate. So hopefully that will kind of help. We also have clusters, again, within groups that we are kind of kicking in a hydrogen here or there. Now, whenever you kick in a hydrogen, what you're going to see is that the charge is going to be bumped down one. I'll show you what that means. And you also have to kind of say, you have to say that the hydrogen's there, quite frankly. Okay, so if your anion has a -1 charge, then it will be neutral. More likely, if it has a -2 charge, it will be bumped down to a -1. If it has -3, it'll be bumped down to a -2. So it's like adding an H+, go figure, is kind of like bumping the negative down 1. So that'll kind of help you there. Some examples here is sulfite, SO3 2-. We have hydrogen sulfite, which actually instead of 2-, it's -1. Another cluster, sulfate, hydrogen sulfate. And if you learned it or would rather use the bisulfite and bisulfate for these two, that works. Carbonate, CO3 2-. HCO3 -1 now is hydrogen carbonate. Phosphate gets exciting because phosphate is PO4 3-, so you can kick in 1 hydrogen and actually 2 hydrogens, and you still have a negative polyatomic anion. So it goes from a -3 to a -2 to a -1 when you kick in those hydrogens. The other thing actually, and I don't know where you want to fit this into, how you're wrestling with this material, this DI, of course, means 2-ish, right? That is the only place in this nomenclature that you're going to use the term di. Sometimes students have learned naming, I don't want to mess you up, but have learned naming molecular compounds, not ionic compounds, and we use these prefixes all the time in molecular compounds. Ionic compounds, we don't use any prefixes except for this dihydrogen phosphate. So again, with the polyatomic ions, you're going to have to memorize what the name means and then what is the charge of that species. So to try to help you, I've got a couple of things, and this is your first of your, and I'll write it up on the board so we're on the same page. I mentioned opportunities for extra credit. This is your first of 2 opportunities, and I kind of told you how they're going to go towards missed assignment points. and I told you how I'm doing it, and it should work out just fine. I added a column in Canvas Gradebook, and it's worth no points, and I just dumped these points in there. And I didn't dump in the points from yesterday, but I will, okay? So for 10 extra credit points, I have a little note to myself, cut these out and take a picture of you with your cards, like a selfie. So you can see a solid line. So you cut along the solid line, and then you fold along the dotted line. And you can hire somebody to do this for you. To do the picture, and actually sometimes I've had students just bring them to, I almost said church, just bring them to school and show them to me and to get your extra credit. That's fine too. Are there any questions about that? So they're very fun. They end up looking, as you might imagine, I think I had my daughter years ago do my set. They end up looking like this. Yay! But now, what I tried to say is, you know, oh, you can make a cation pile, an anion pile, and what I started to say is, you know, I have a BR-1. Do I? No. I'm fine. Bromide, I think I'm okay with that. So you might want to kind of pull out what you don't need to wrestle with, okay? The other thing, I think we're about done with this, aren't we? The other thing I want to show you right quick, if I can find it, is something I showed you before, but I want to show it in a different context. If you, and I can never spell mahjong, but if I chemistry mahjong, oh my goodness, something like that, it'll find it. It always does. Okay, there's this thing from Stetson University, and I showed it to you before because we were kind of learning the names of the elements and all that. But also it has a polyatomic ion feature. This app, by the way, is available for Android and for iPhone. So the way this works is we are going to change the game to polyatomic ions, start a new game. You can go with different shapes, and remember how Mahjong works is you have to find two available things. So here I have a, let's see, that's a sulfite. That'd be SO4. Anybody see a pair? Oh, here's nitrate. I'm going to go with nitrate. So nitrate, and I know that's NO3 minus 1, and they're both available, and they go away. It's kind of potentially addictive. So you try to clear your board by finding pairs. So there's that.